Okay, good evening, everybody. Let me turn on my camera. Yeah, I'm visible now. Am I audible?
Yes, sir.
You can turn off your microphone and speakers also. Okay, so we are going to see some stuff, which is, let me start with our web page for WiSSAP. You can see my screen now, right? Okay. So this is the WiSSAP web page you must have seen, and if you go on the top, you will see WiSSAP Cup. This WiSSAP Cup has two competitions. One is music search, other is so basically one is query by example, the other is query by humming. So in today's talk, I'll be discussing these two problems in I will be introducing you to these problems and what are the relevance of these problems, and what are the applications, and what are the different approaches to these problems. The timeline is like this. As you know, we will be you have time to learn about the problem, develop your solutions, test the existing solutions, and develop your own solutions. And so by 30th of October, which means we almost have 1.5 months, means you have almost 1.5 months to learn about this area, to develop things around this area. And then we'll release the final test set on 30th of October. And after that, the final submission will be there. And we expect that by 6th of November, the results will be also announced. Okay, and all these are other logistical details which you can see on this web page. Now I would like to go on. So what is the purpose of today's talk? The purpose of today's talk is to give you an orientation that how this problem can be approached and how you can build your solutions very nicely. I will share my slides now. So you're able to see my screen. Okay, say yes if you're able to see my screen. Can you see my screen? Okay. Okay, you can speak, I can hear.
Yes, sir, we can see.
Okay, thank you. Yeah, let's keep it interactive because I don't know what is the background of the students here. It's possible that you come from very diverse backgrounds and you may have no idea of some of the things which we are discussing, but use this time to ask questions. We have 1 hour. Use this time very efficiently, ask lots of questions, and make sure that you know the things inside out. Okay. Okay, so we are discussing now about this WiSSAP Cup 2023. The theme is audio search. What do you understand by search? Search means you have a large database and then you have a query. And this query could be a very simple, short kind of entry, and you want to search based on this entry from the database other entries which are similar in some respect. So for example, you all have used text editors, and my query is a word, which means a text string, and my database is the entire document which I am reading, maybe a Python code or a Word document, right? And then I want to search that particular word. And all of you know how useful it is, right? Whenever you want to search a word, you just type it there on the find bar, and then it just takes you to all the occurrences of that particular word in the entire document. So an example is this. Let's say this is my Python code. I type a query in the search box. The query is called plot, and it will search, or it will retrieve all the instances of plot. And I can use up and down buttons here to navigate, right? So, but this is exact search, which means this is exact search. Just a moment. This is an exact search, which means my query has an exact match in the document. Now, what about, okay, Google text search? In Google text search also, you give a term, let's say IIT Kanpur, and the database has all the web pages on the internet, and it will retrieve occurrences of IIT Kanpur. Now, sometimes this search could be inexact also, which means I may have some spelling mistakes, but still that search engine would try to find the best possible matches, right? So all these fall under the category of exact search or nearby search. And what are the different types of algorithms which exist in literature for search? If you have done a course on programming, data structures, algorithms, there you may have come across these algorithms like linear search, bubble search, binary search, tree search, graph search. So all these algorithms exist for exact search, but we are not interested in exact search, right? Means exact search is a very very much like solved problem, maybe we can say, or at least we are not interested in that, okay, even if there are challenges there. What we are interested in is called the problem of information retrieval. So what is that? So all this which you see here, like what is IIT Kanpur famous for? What is the rank of IIT Kanpur in the world? Does IIT Kanpur accept JEE main score? Like, so which means in the document, there may not be an exact occurrence of this sentence, like what is IIT Kanpur famous for? No document may contain this entire sentence exactly, but you know what I mean. When I'm asking for what is IIT Kanpur famous for, I don't want to see the location of IIT Kanpur. I don't want to see the number of students in IIT Kanpur, but rather I want to see what are the areas of research or areas of education in which IIT Kanpur is really famous. So this is called information retrieval, when my search and my query, they are not exactly same, like the tokens are not exactly same, but they have a same semantic meaning. Now the search could be either a text search or an image search, audio search, so many modalities could be there. For the underlying goal for all these search methodologies is, number one, efficiency, that the search should be done very efficiently. Like if you do Google search, it will show you on the top that this query took 0.00001 seconds to search, to retrieve the documents. That means it is very efficient. Like you just press enter and immediately the results are in front of you. But if the algorithm were inefficient, it would have taken 1 minute, or maybe a few minutes, or maybe 1 hour to retrieve all the relevant documents. And then everybody would have said, oh no, this is not a good system. Nobody would like to use such a system. The other thing is efficacy, which means how relevant are the items which are retrieved. I searched for what is IIT Kanpur famous for, and it is retrieving things about, let's say, how many students are there in IIT Kanpur, or what is the location of IIT Kanpur. Those are not relevant answers or not relevant documents. I want to get very efficiently, very exactly what I searched for. The general formulation is that I have database capital Z, and there are entries in it which are small z. Then I have a query small q, so which is also in the d-dimensional space. Like my entries are d-dimensional, queries also d-dimensional, right? And I have to return an ordered list. Ordered list means like this is the top hit, second hit, third hit, just like you see in Google search, right? You get a list of all the retrieved web pages, and the best match is on the top, and then second best match, third best match. So it's an ordered list. Now let's come to audio search. What is audio search? In audio search, what happens is we have a large database, not of text websites, but it is audio database, which means I have a large database of audio files. Each audio file could have any duration. Some audio files could be 1 minute, 5 minutes, 10 minutes, 20 minutes, half an hour, 1 hour, even longer, right? So different lengths of audio files in a huge database, maybe gigabytes or terabytes of size. And now I have a query, which is a small segment, right? Which could be just a small segment of my, let me take out my pointer. My query is just a small segment of original file. Let's say here I have a long song, maybe 5 minutes song, but somewhere I got a small snippet of that song. Maybe I heard it on television, I just recorded it on my mobile phone, or I hummed it myself. I sang it myself, and I have that recording, right? So it could be a noisy version of the original song, like I recorded with a mobile phone when the song was playing on television, or maybe in a party, and I just recorded it. So now using this query, I need to retrieve this file from a very large database of audio files. How do I do that? So in general, the approach could be like this. You take a kind of feature extractor, or a kind of fingerprint extractor, or some embedding extractor, or representation extractor, which basically converts your long audio file into some very compact representation. In this compact representation, it could be vectors, like it's a sequence of vectors which are extracted from this audio file, or it could be single vector, multiple vectors, etc. Basically, it's a compact representation of the entire audio file. And this algorithm or model I apply to all the audio files, and I extract these representations for all the audio files. And then the same extractor or a same model I apply to my query also, and I get some representation, right? So now I have obtained all the compact representations, because searching in the large representation is difficult, but searching in some compact representation is very easy. So then we need a matching algorithm which will compare these representations and give you the nearest match, the closest match, or the best match. And the goal is that this matching algorithm, so basically this representation should be so efficient, and then this matching algorithm should be so good that finally you should be able to get the required document, which exactly you are looking for. We call it as the target document. Let's say every audio file, if you call it the document, then this is my query. I want to retrieve the target document. I could also retrieve a list of documents based on my matching score, like the top match, second best match, third best match, etc. So basically, we see here, there are two main components of our search algorithm. One is the feature extractor, the other is the matching algorithm, right? Okay, I take a small pause here. Please tell me if you have any questions. Do you have any questions at this point? Just unmute yourself and start asking questions.
Sir, is there any particular algorithm which we are applying for this matching algorithm, like pre-existing algorithm?
Yeah, I will discuss that. I will discuss several algorithms in my talk
Okay, sir.
today. Yeah. Any other question? No?
So do we need to remove all those noises and extra like disturbances before applying these algorithms?
Yeah, yeah. It could be any method you may try. You may try a noise removal algorithm. Basically, this F, it could be a combination of many things. Like you can have a noise removal algorithm followed by some compression algorithm followed by something, something. All those things are kind of in this F. But what we use these days is a neural network, which will do all that for us automatically, which means we train this network in such a way that these representations match, right? So which means denoising, dereverberation, feature extraction, etc. Everything is done by this model, which could be neural network, which is trained in such a way that these representations match. Okay. Yeah. Any more questions? Oh, okay. Let's discuss very basic. What is audio? How many of you are familiar with audio signals? Yes. Nobody. If that is the case, then I would like to tell a bit about what is audio signal. It's very basic, but I hope you will benefit from this. So what I'm going to do is I'm going to open a simple platform called Prat. Okay, this is a very simple software which you can install on your machine, on your computers, and you can use it for audio processing, etc. So, and let me record a sound. E, E. Okay, I will save it to the list and close it, and then now I will open. Okay, I have to share the entire screen probably. Let me share my entire screen. Where do I share? Okay, this is what I got, right? When I said E, then you can see this is how my audio looks like. When I say let me zoom in. It's basically a time series. Like when I E, this is the E sound. E. So this is the E sound, and you can see it's a periodic waveform, right? If I zoom in further, you can see it's a periodic waveform. So what is the periodicity? You can see that this peak and this peak, what is the length of this? What is the distance between them? So it's 2.41, it is 2.40, so almost like 0.01 second, something of that sort. And to find frequency, you can take 1 upon the time, that becomes frequency in hertz, right? So you can turn on show pitch. Now the pitch here is 146 hertz. You can compute it yourself also by just computing 2.411 minus 2.4037. And this is the time period. Take 1 upon time period, that is the frequency. And this will come out to be 146.8 hertz. So which means this is a periodic signal with this much frequency or this much time period, and it's repeating. Now, whenever we have a periodic signal, we can compute the time period, and then we can also compute the spectrogram or the spectrum. So what is spectrum? Basically, let me show you what is the spectrum. this is how the spectrum looks like. You can see this screen. So you can see that there is this, let me zoom in here. So there is one peak here. Okay, I think my window size is very small. Let me change it. Show spectrogram settings. I will take a large window size. Window length is, let's say, 50 milliseconds. Okay, now I plot the spectrum. Select. Okay, you can see there is a peak at that same 140, 150 hertz. Then twice of that frequency, then 3 times of that frequency. So these are called the harmonics. Because if my signal were a perfect sinusoid, I would have gotten a single peak here of at 140 something, 148. But since it is not a perfect sinusoid, it's a distorted sinusoid, you can say. So we get multiple harmonics. And these are the harmonics. Like this is we call it F naught. F naught frequency is 148 something. Then 2F naught, 3F naught, 4F naught, so on, maybe 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So all those F naught, they appear as peaks in my spectrum. Generally, we take these spectra, like we take small windows of my signal. Like I take this small window, I compute the spectrum, and I plot it like in this vertical direction, which means the y-axis is the frequency, x-axis is nothing, it's just the time, and height or the brightness or the intensity shows me the value of that or the energy in that frequency bin, energy in that region, in that frequency, you can say. So, and I take these small windows and I keep plotting it one after the other. I keep placing it one after the other. In this way, I get a complete spectrogram. This thing is called the spectrogram, which means a series of spectra, series of spectrums, you can say. That is a spectrogram. Is that clear? Does that help? Or do you have any further questions? Okay, if not, then I will move to next part of the presentation. New share. I'll go back to my slides. Can you see my screen now? Oh, sorry, I stopped sharing. My screen visible? Okay, yes. So this is basically what is audio. It's very important that you understand your domain before you start working on machine learning concepts directly. Okay, so that's what I was telling. You have audio is a long waveform, and you split it into small windows with some overlap. And from every window, you extract some spectrum or some other acoustic parameters. Generally, these are spectral parameters, means you extract the spectrum and then maybe take small bins. And in those bins, you compute the energy so that you can get some compression. Okay, so those details we can see later. Now, whenever you have a periodic signal, you know there is a fundamental frequency F naught. Like we saw in the previous example, it was 148 hertz. That was the fundamental frequency, which means the frequency of which we had harmonics in the signal. You can calculate the frequency by using autocorrelation or spectrogram or spectrum, etc. Different methods are there. Now, this is a very important slide. So if you really want to work on speech or audio, then this is a slide which you must understand. So whenever I speak, it's a periodic signal. But what we assume is that it's like a source filter model, or in other words, it's a linear time invariant filter. So basically, it means when we have my xn. So what is linear time invariant filter? Basically, it's a filter which is linear and time invariant, and the input is just a periodic signal, which means, do I have a pen here? Let me just use my pen to write. Yes. Yes. So let's say my input is just peaks. This one, then this one, then this one, then this one. It's a periodic pulses. This is my input into a filter, which is a linear time invariant system. And it gives me the output, which is the audio signal, right? These are just the periodic pulses. This is an LTI filter, linear time invariant filter. So basically my audio Y of n is X of n, which means this one, this is X of n. And this LTI filter has an impulse response H of n. This Y of n is simply a convolution of X of n with H of n. If you're not familiar with the linear time invariant filter and this kind of analysis, then I would recommend that you can read a bit about it to get an appreciation for this concept. So now why I'm telling you this way. So here we have decoupled the information. This X of n contains the frequency information or the F0 information. And H of n contains the phoneme information, which means what I am saying. So let's say when I sing music, I say, I said the same phoneme, but with 3 different frequencies or 3 different pitch values, right? So when I say, it's a lower pitch, higher pitch, even higher pitch. So in this way, my pitch is different. So now if I use this formulation, I can decouple. I can just extract a compact representation that, okay, what is the pitch of my periodic pulses? And that will tell me what note I am singing. On the other hand, if I'm interested in the phoneme information, I don't worry about what note you are singing. I'm not interested in the musical, melodic part, but I'm only interested in what word you are saying, whether you are saying or e or u. Then I would rather look at the H of n. So in frequency domain, what happens is my X of n has a Fourier transform, which is like periodic pulses. And my H of n is a filter which has some shape like this. And when you convolve them to get the final audio, convolution in the frequency domain becomes product, right? Which means you multiply X of k, or the X spectrum, with the H spectrum. And this product gives you the Y spectrum. And this Y spectrum looks like this. You can see that this has a like H thing multiplied with the X thing. Like this comb is multiplying with this smooth shape, and it is giving you a smooth shape, but with a comb here, right? So this is how the Y looks like. Now, if I change my frequency, then saying the same word, then how will my spectrum change? The smooth kind of envelope remains the same, but the comb distancing changes, right? So I will repeat this point. This is very important. So the spectrum of my final audio, YN, how does it look like? It has got this comb-like structure, which means F0, 2, F0, 3, F0, etc. All those peaks are there. And it has a smoothly varying envelope. So if you are interested in the frequency information or the melodic information or the musical information, then look at the distance between the two comb teeth, right? Or the two peaks of the comb. This distancing will tell you the fundamental frequency or what note you are singing. But if you're interested in the phoneme information, or whether I'm saying or e or u, then look at the envelope. And this envelope will tell you what you are singing. And you can see in this figure, when I say as in father, and in the envelope looks like this. If I say E as in heed, the envelope looks like this. You can see here the first peak and second peak are very close. The peaks in the envelope, not in the F0 to F0, but in the envelope. The first peak and second peak are very close, and here the first peak and second peak are very far apart. And likewise in U, you can see first peak, second peak are close and like on the lower side as compared to A, but the third peak is very far apart. So this shows you how the envelope changes when you speak a different phoneme. This is called a source filter model. It's a very popular model for analysis of audio sounds, audio signals. And if you understand this, then you understand audio much better. Okay, any questions at this point? At this point, do you have any questions?
Sir, how will we generate that accent part of any audio? Like, do we need to generate it by using any algorithm, or
No.
will we get?
In this task, you don't need to generate XN. You have YN already with you. Like database is full of so many YN, and queries also YN. But this analysis will help you if you are doing task number 1, which is query by example. Then you are interested in the maybe the phonemic part of it, and maybe also in melodic part. But if you're doing task number 2, which is query by humming, where I'm just humming a song, then I am not concerned with the phoneme information. I'm only concerned with the F0 information. And that information, how do you get it? Look at the spectrum of your audio, look at the spacing between the comb teeth, and that tells you the F0, and that F0 can help you search for the right song, right? So in this task, you are not generating any audio. You have the audio, just analyzing it. But to analyze what kind of features you want to extract, this is what this slide is helping you with.
So the envelope part is from YN, right? That's the output which we are seeing, right?
Yes. Okay.
And
so
as you, sorry, sir, as you said that output already we are having loads of data, right? So this we are just doing for the ease of analysis, right? How we can further process it to understand.
Yes. So you have audio signal, but it is assumed or it is modeled that it is made up of these two components. You have something called Xn and H of n. And there is also some physical semblance to it. The physical interpretation is that when you speak, you make your lungs produce some air, and this air, when passes through your vocal folds, the vocal folds vibrate and they generate these periodic pulses. And when that sound, the periodic pulses, which is a kind of sound, when it passes through your vocal cavity, which means your mouth, your nose, and the teeth and tongue and everything, then depending on the shape of that cavity, that cavity acts like the LTI filter. And whatever comes out, it's the audio, right? When I say O, I am rounding my lips, different kind of cavity. If I say E, I am stretching my lips, different kind of cavity. When I say A, I am opening my mouth, or my tongue goes down, and so A sound is generated. So the vocal cavity is different, right? So this is a physical, you can say, interpretation. Okay. Any other questions? Okay, then I will move forward. Okay, what are the applications of audio search? Now we are coming back to audio search problem. So now you already have seen what is audio. Now let's talk about audio search. So what are the applications of audio search? For example, music identification. You have large database of music files. You want to identify, or you want to search for some music. One way could be if the music has some metadata, which means some text information connected with that file. Let's say I save a file, I give it a name. Maybe this is the Jana Gana Mana, or maybe I fill the metadata in the it has some fields along in the file. Let's say there are some fields that the frequency is 44.1 kilohertz, etc., etc. So I can search using those fields. I can search for, okay, I want Jana Gana Mana. So wherever the Jana Gana Mana is there in the text, it will retrieve that audio. But that's very limited way of searching for music. For example, if you work with Hindustani classical music, there are different notes, and you don't write notes. When you let's say you have alap, you won't even have words for that. You just have notes after notes. And how do you write? You can't write it in a simple way. Nobody writes it as a file name. But what you can do is you have to analyze the music audio itself to find the best match. Then another application could be in broadcast monitoring. Let's say there is a broadcast station, maybe a television channel or something, which is broadcasting so many things. And you want, let's say there is an advertisement company, it wants to monitor how many times my advertisement was broadcasted so that I can pay. And also when it was broadcasted, for how long? Did they run it in the full length, or did they abruptly stop it in the middle? Then based on that, the company will pay the advertisement or advertising company will pay to the broadcasting company. And another application could be, let's say you have very large data sets and you want to search for some particular audio. For example, I want to search for gun sounds. Then I just upload an audio file with a gun sound and it will retrieve all similar gun sounds. Another use could be in education. I have lots and lots of audio lectures, video lectures. Videos also contain audios. And I want to search for some particular keywords. How do I do that? So using this technology, which you will be building, so you can make this system. And if you apply it on the lecture videos, lecture audios, then you can simply search for a particular keyword. Let's say I'm learning machine learning and I want to know what is regularization. And in the title of the lectures, nowhere it was mentioned regularization. So one very simple way could be I just say regularization, and wherever the prof has said regularization, all those occurrences will be retrieved by the algorithm, right? And this could be in any language, not just in English. It could be in Hindi, it could be in Marathi, Punjabi, Bangla, so many languages. So, okay. What are the challenges in audio retrieval? Number one is robustness. There are so many audio distortions. There could be noises, there could be reverberation. Because what is noise? Let's say you record with a microphone. Microphone is an electronic setup, and microphone has got its own electronic noise. That is one kind of noise. Let's say you are recording in a party, and there are people also talking in the vicinity. Then those people will talk, and those sounds will also get picked up by your microphone. So they act like noise. Those sounds act like noise, right? So these are unavoidable noises. And reverberation. What is reverberation? Reverberation means, let's say you are in a closed room and there are walls. So because of the walls, there will be reflection of sound. And that reflection will again be picked up by the microphone. So this is reverberation. So all these things are quite unavoidable in real world settings. That's why we want our algorithm to be robust against these audio distortions. And then we need very high efficiency to expedite the retrieval process. Imagine you have millions of documents or millions of audio files in the database, and you want to retrieve, and your algorithm take 5 minutes to retrieve, which is, you will say it's a very good number. Like in 5 minutes, you are able to search 1 million audio files. But from a user perspective, it's not a good thing. Imagine you are sitting on Google and it takes 5 minutes to do one search. You will be really frustrated and you will not like to use Google then. So efficiency is important. The next is less complexity for practical deployment. We want our algorithms to be less complex, which this complexity could mean computational complexity, which means how big a CPU or GPU or whatever I need to deploy the system. For example, if I need really, really big RAM, a system with a big RAM, then that's not a very good system. It will cost so much, and nobody would like to have such a system. And then complexity could be in terms of memory complexity. So I discussed in the beginning that I want to compress my audio files to such a small length, such a small size, so that the search becomes very efficient. But if the size of that compressed representation is very large, then imagine when you do it for 1 million audio files, it will become really scaled up by 1 million times. So I want the representation to be very compact. And also my search algorithm should be very less complex. It should not use so much of memory or computational resources. Okay.
I am running.
Okay, now what do I mean by compression? When I say this sentence, I am running.
I am running.
It says I am running. Now, traditionally, there have been ways to write it in a compressed form. For example, this I am running is a combination of many phones. A, I, E, M, R, N, N, I am running. It's made up of many kinds of phones. And these phones are not the written form, but the sounds, different kinds of sounds. And then comes phonology, where they see everything in terms of phonemes, not phones, but phonemes. Now you can see this and this could be very different in different phones, but in phonology, they become same. This and this are same because they both represent same linguistic element. And we don't need to distinguish between them. We never distinguish between these two. Therefore, they are kind of clustered together into one unit or one token. And then you have orthography, the way which you write language, like I am running. This is the textual form which we deal with. Then there could be a morphology to it. Once you have the orthography, you can do further analysis in terms of morphology, etc., which means run is made up of run plus ing. Running is made up of run plus ing. So run is the root word, ing is a suffix, and it becomes running when this suffix acts on this root word. And then there is syntax, there is semantics, there is pragmatics, and then there is the kind of real thing which you understand when you hear the sound I am running. So all these different levels of representations are there. So which one is a very compact representation? So that is called, maybe let's say orthography. This is how you write the sentences, right? You use a text. Google works with orthography, which means Google searches in the orthography. Why? It's a very compact representation. That's why not? And it distinguishes sounds as they carry different meanings. It can be used for further analysis, etc., etc. So orthography is a very good thing to do. Can we do automatic orthography? Can we convert sound to orthography automatically? ASR does it, but ASR is already it's a supervised system, which means ASR means automatic speech recognition. That is what Alexa does. That is what Google does, or Google, OK Google does, or Siri does, or Bixby does. So all these systems, they do speech recognition, which means they convert audio to text or speech to text. And this text is basically the orthography which was defined by some people, or which has traditionally been used for those languages. But many languages may not have orthography. There are so many languages in India itself which don't have orthography. I know some languages in Northeast, at least, they don't have orthography. Some languages in Himachal Pradesh, at least, they don't have orthography. And I am from Punjab. Even in Punjab, there are so many dialects and they don't have orthography. What about music? Music doesn't have an orthography. Okay, it's very non-standard. At least in Indian music, means we don't have exactly an orthography. People have tried to devise some methods, but then there is so much of variation even within that. And so music is like, you can practically say it doesn't have an orthography. Although in Western music, they have evolved a sense of orthography there, means notation system is there, but that notation system is also kind of very limited representation of music. What about bird sounds? What about environmental sounds? So many kinds of audio are there. So they don't have orthography. So these methods which we are building in this challenge, they are useful for audio search. Now, okay, with that, these are the concepts which you may need for solving these problems, to solve these two problems. For example, you may need some background in machine learning, some background in audio analysis. So you can go through these YouTube lectures. I will share these slides with you. Akshay will share them with you, and you can go through all these links. So you can use dense neural networks, convolutional neural networks, recurrent neural networks, and a concept called dynamic time warping, and a concept called locality sensitive hashing, or LSH. These are very useful concepts you may learn. Now, somebody asked about the tools which we can use. Yes, there are also already existing tools which you may look at. For example, one search method is called Neural Audio FP, and this is the codes are available online. You can go through it. It uses neural networks for audio fingerprinting. I will also add another link, actually. Shazam system. It's also, the codes are available online. You can just have a look at them. Don't use that as it is. That won't serve any purpose, because we already have that baseline with us. So if your results are as good as the baseline, then you didn't do anything. So you have to improve upon that. Okay, then tools for indexing and retrieval. Now this algorithm can generate representations, but how do you index them? And matching algorithm, right? Matching algorithm means you have to index them, means put it in a very easily searchable form, and then retrieval means doing the actual search. So that is, there is a library called FAISS library from Facebook, which you can use. Yeah, you can use it as it is also, no problem. Or if you want to make your own algorithm, that's also very much welcome. Now, I will discuss quickly about audio representation learning. So you have got, I'll skip some mathematical details here. So basically, you want to convert this audio into either a vector representation or an orthography, or basically a tokenized representation. It could be written as with the help of characters, or with the help of some numbers. It could be anything. So this is the representation which we want. Of course, this is much more compact than this. And one very popular audio search system is called the Shazam system. It's a rule-based system. All of you know, you use Shazam in your mobile phones. This was the first algorithm which Shazam started with. It's a rule-based algorithm. It looks at the spectrogram. I hope you remember the spectrogram which we discussed. And then it looks at the peaks in the spectrogram. Like wherever the peaks are appearing in the spectrogram, it will pick those peaks, it will make some cluster of them, and it will represent it in a very compact way. And then it will search for such clusters. Means the clusters in the query will be matched with the clusters in the target audio database. So this was the Shazam algorithm. The algorithm is available. The paper is also available if you want to read. There could be unsupervised methods to learn representations like SIBO and skipgrams. These methods were developed originally in text representation learning, like word to vec, BERT, what else, Hubert. So many systems are there which convert words into some vector representations in a self-supervised way. So this is, and also all of you are familiar nowadays with ChatGPT. So ChatGPT is also built on these principles of self-supervised learning. I will skip it. If you have questions, you can ask. I will present them in the next lecture probably. And likewise, we have something called wave to vec, which is a kind of inspired from word to vec model, which was word to vec was for text, wave to vec is for audio. So basically, it learns a representation. That's it. So you can use a neural network to generate the representation also. For example, here we have a signal xi. It's a one spectrogram, and xi dash is a spectrogram of a noisy version of x. Like you have some audio, you can artificially add some noise, some reverberation, etc., etc. And then you train your system so that the representations for this original sound and the representations of this noisy sound, they are very similar to each other. And this loss function kind of is minimum when they are exactly same. And the loss function has got a very high value if they are different, right? So our machine learning, what it tries to do is it tries to tune the parameters of F. Let's say if F is a neural network with W weights or parameters. So our optimization algorithm will tune these parameters so that this loss function is minimized, which means my F of xi becomes very similar to or almost same as F of xi dash. Means the clean audio and the noisy audio, they have similar representation so that we can search quickly. There are some papers from our lab, you can go through them. And actually, Anoop is the one who has written these papers, and he's also the one who is coordinating this task. And likewise, Adhiraj has written some other papers. He's also coordinating the other task. So both of them are available to you. You can ask questions. Now, the next topic is, so right now, just now we saw representation learning. Now we are going to see indexing and retrieval. How do we save those representations in an efficient way and so that we can retrieve very quickly? How do we retrieve, very simple question, how do we retrieve a vector or a scalar? Let's say I have my database consists of decimal numbers or real numbers. My query is also a real number. I want to retrieve the nearest neighbor. Right? So how you will do it? Okay, you have your search algorithms. You can, so my retrieved list will be something like this. 1.67 is the nearest neighbor. 1.03 is, okay, close, but not as close as this, but second best probably. 2.18 is the third best. In this way, you will get a long, long list. This is how retrieval, this is the goal of retrieval algorithm. Now, if you extend it to a vector representation or a high dimensional representation, then let's say this is my data sets, like different entries or documents in the data set, and red one is my query. So you can see Euclidean distance. So the distance between this and this is the minimum. So my algorithm should return this as my top hit. Maybe this one as second best hit, this one as third best, this one as fourth best, this one as fifth best, etc., etc. So generally, this algorithm, the nearest neighbor search algorithm, has a very high complexity because this query will be matched with every document in my database. And if we have 1 million documents, then doing 1 million matches will be very time consuming. So there is an algorithm called LSH, locality sensitive hashing. So what it does is it will break your entire space into small, small compartments or small, small buckets. And so that things which are close to each other, they lie in the same bucket. Of course, there could be boundary effects, but ignoring those boundary effects, let's say this is my query, the diamond is my query, then I will not compare it with every entry. I will just find out which bucket does it lie in. And then I will just go to that bucket and find my nearest neighbors only in that bucket, right? So you see that how much efficient it becomes. Now, how many buckets could be there? It could be like thousands of buckets, right? Which means my search time comes down by 1,000 times. Like let's say if I have 1 million entries in the database and there are 1,000 buckets, then every bucket will have on an average how many? 1 million upon 1,000, which means only 1,000 entries, right? So instead of matching with 1 million entries, now I'm matching with only 1,000 entries. So my search time has come down by almost 1,000 times, right? So which means if my algorithm is taking 1 second with this LSH, it will take, let's say, almost like 1 millisecond, which has a very good effect on the users. So locality sensitive hashing, I will skip these mathematical details. Okay, now the problem in audio search is not simply retrieval of scalars or vectors, but rather we have a time series or a sequence of vectors or scalars or a time series of tokens. So for example, my query could be EFGH. Let's say you have your audio file, you have compressed it into some representation, and this is EFGH, let's say. And my search space has long strings, and I want to find the best match. Now see, it should retrieve this document first because it has EFGH in it. Now this has got EIGH, which means one thing does not match, but other three are matching. So it may also retrieve EIH, means a document containing EIH, which means it is further far apart, right? So this is something. This is something what we want. If I can represent my audio in terms of these sequences, then my retrieval is in terms of sequence matching, not just vector matching or scalar matching, but it's sequence matching. And how do I do sequence matching? For sequence matching, I can use edit distance or DTW, dynamic time warping. I have shared the link with you. If you want to know the details of DTW, they are available. But this figure just shows you in short what is meant by DTW. Let's say you have something like this inverted U. Let's say U. This is like a U-like shape going from time equal to 0 time to 100, a U shape. And this is my, let's say, this is my search space, something. Then I have the U here, right? DW, what it will do, it will match every point with every point here, and that distances are plotted here. And yeah, you can read the details there. Okay, this is dynamic time warping. It looks at the point-wise differences and then finds the best path, etc., etc. Okay, now let's come to the evaluation metric. This is the last part of the presentation. Okay, you made an algorithm which is doing very nicely. Okay, now how do we evaluate? How do we compare whose algorithm is the best or whose method is the best? One evaluation measure is MRR, which is called mean reciprocal rank. So let's say QI is our ith query, and DI is the target file which matches this query. And the algorithm gives me a list of retrieved documents, and I will look at the rank of my document DI, which means my target file, my target document DI. And what is the rank? Is it 1, 2, 3, 4, so on? Let's say if it is 3, then RDI is 3. Then what is MRR doing? MRR will first of all invert the rank, which means it becomes 1 upon 3. And then it will average over all the possible queries or all the queries in my evaluation system. So let's say I had 100 queries. For the first query, the rank was 3, so it became 1 upon 3. Plus for the second query, my rank was, let's say, 10, so plus 1 upon 10. For third query, rank was 1, so plus 1 upon 1. And I take the average of all of them. That becomes the MRR. Now, imagine if my algorithm is really perfect, which means every time my document is retrieved at the top, so which means always its rank is 1, then it is average of 1 upon 1 plus 1 upon 1 plus 1 upon 1, so on n times. So when you take the average, it is 1 only. So 1 is the best you can achieve. And anything lower than 1 is kind of lower. So higher is better. Another thing which we want to check here is the retrieval time. How much time my algorithm takes to retrieve these the documents. So if my algorithm is taking long time, that is not good. So lower T is better. And so this is the average retrieval time taken per query. So let's say if I have 100 queries, then the total time taken divided by 100 will give me small t. And the final score on the scoreboard, on the leaderboard, will be computed as 0.77 times MRR plus 0.3 times exponential of minus AT. This A factor we will decide. We will keep it uniform for everybody. We have not decided the A factor yet, but this A will be decided so that both get equally weighted. Not equally, but okay, proportionally weighted. And finally, the score should be high. The higher the score, the better your algorithm is. So that's it, I think. Thank you very much. If you have any questions, I'll be happy to answer them. Okay, Kaustuv is here. Hi, Kaustuv. Please.
Hi, Vipul. Great talk. Very nice refresher for and I can imagine how important this is for the student. So I found it very useful. Was also good for me to go through all the criterion. Maybe I'll get in touch with some specific questions later. But for the query by humming, do you also facilitate the key transposition invariance or those kind of things? Like you hum in a different pitch
Yes.
and a very different tempo. So what is the constraint that DTW will be allowing? Do you have any guidelines on that, please?
Yes, we can discuss in the next talk more about these details. So basically, for everybody's benefit, I'll just repeat what Professor Ganguly meant by that. So when I'm singing a song, I may sing it at different pitch. Maybe Kaustav can give an example. He's a singer.
No, you please go ahead.
No, you please.
Okay, like for example, people who was mentioning Jana Gana Mana. Now, if you sing da 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 da, now the same intervals will hold true if I sing from a different key. Say, for example, da 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 da. The same intervals hold true. But if the database has a single pitch recorded, and you are querying from a different pitch, would that allow? And would that have to be aligning to one of the like A440 grids so that you do the transposition? What if it is not on the grid? What kind of adjustment it needs to do? So if that is part of the challenge.
Yes. So pitch shift is certainly very challenging, and it's very practical to address that. So it's a very real world problem. So we will definitely have pitch shift in our database included.
Okay, great. And it can also be non-grid, like for example, something between C# and D. And if it is like way off, then you have to have maybe a resolution of 1 cent. So you have to do 100 searches between one semitone. And if you have to do for all pitch values, it's like 1200 computations for the same matchmaking.
Yeah.
Okay, so
yeah, I will discuss in the next talk about some existing methods to deal with this problem. One method is that you don't take the absolute value of pitch, you take the relative change. Let's say if I sing da da da, then say that, okay, it's constant, and then it makes a jump by this factor. Let's say it becomes 1.01 times. And then it makes another jump after some time, again 1.02 times something. So
right.
Only relative changes are stored as a representation, and this can help you avoid all those problems of cents and absolute grid.
Yeah, sure. So, and also, for example, we don't know the quality of the query. If the singer is maybe an amateur singer,
yes,
and doing some pitch which is not correct,
yes,
so then it might also fetch another song.
Yes.
Now the thing is, semantically it's not correct, but syntactically it's correct, because the audio acoustic features you are keeping as a query exactly matches or are more nearest in the neighborhood of another song. So how do you evaluate that? Like, do you have any quality index of the query, how representative that query is?
We have prepared a database in our lab on our own, and yeah, I think this is an issue which we have just told our singers, or they're all amateur singers, they are not expert musicians, so they will make mistakes, but we have asked them to sing as faithfully as they can. But yeah, I think
because the semantic error is something which is interesting, and maybe some good insights may come out.
Yes.
Because if you take maybe all Bollywood songs of a certain era, there are a lot of overlapping tunes.
Yes.
And maybe certain one change of note, which is equivalent to one edit distance, it can fetch another song, which is doing the right job. But because your like answer is a different thing, you lose a kind of mark in the evaluation.
Yes.
So how to tackle these kind of boundary cases?
Yeah.
Would be interesting.
Yeah, definitely. We will also learn in this process. Yeah, thank you.
Great.
And the other thing which you mentioned was the timing, that how is the tempo. Let's say I can sing like faster or slower.
Yeah.
So it could be slower or faster. So this will also be a challenge in query by humming.
Yeah, sure. And also maybe just for a reference for the students, in DTW, you also have to create a constraints. So normally we do twice the tempo or half the tempo. Then it's easy to tackle the path. Otherwise, it might go full horizontal or full vertical, and then it will not converge.
Yes, yes,
So
yeah. So
and one quick thing, if I may, are there any timbre related tasks also, or
no, but the query by example could have timbre information also, because here we have a snippet from the song plus some noise and distortion, reverberation, etc. So the timbre matching also will be helpful there. So it will have no pitch shift, no temporal stretching, no, only noise and reverberation.
okay. So you are artificially creating the queries by incorporating the distortions.
Yes, yes.
And how would that noises be? Like, can it be colored noise or maybe like platform noise or?
Yeah, we have mentioned it in the web page, like what kind of noises and what is it called, the reverberation parameters we are using. And if something is unspecified, then feel free to ask.
Sure, I'll go through that, but just a question. Do you also have a pseudo-random baseline or a human baseline for such cases? Because the intelligibility sometimes get spared for certain kind of noises. So maybe what are we comparing against?
It's a good point. That we should make some human baselines also.
Yeah, I think for the competition's sake, or maybe some pseudo-random baseline, like just apply a transform and by chance it gets detected. But is it really doing the task? Because we are also, like, as you stress on the fact that we are interested in the learning representations. So it's not only the task we are achieving and the accuracy, but also maybe showcase what are the representations and the insights thereof.
Yeah, that will be interesting as well. Yes. Yeah.
Sure, thank you, and look forward to being there in WiSSAP. Like, feels like we are back in the winter school. Thank you for the great talk.
Thank you very much, Kaustav, for your interesting comments and questions. Thank you.
Sure.
Okay. Anybody else wants to ask something? Otherwise, we'll close the session now. Okay. Fine. We'll close it now. See you in the next session. It will be announced soon. Thank you. Bye.